In this video, let us learn about the auditory pathways. Now, auditory pathways are the pathways which are transmitting the special sense of hearing from the internal ear all the way to the cerebral cortex. This is the pathway which enables you to hear the sound, localize the sound, identify the sound, and comprehend the meaning of the sound. Before we begin with the auditory pathway, let us quickly refresh our memory about superior olivary nuclei, cochlear nuclei, acoustic striae, trapezoid body, and the lateral lemniscus. You will recall that you had seen all these structures in the section of the pons taken at the lower level. You will now know that all these structures form a part of the auditory pathway. Now, coming to the superior olivary nuclear complex, it includes a bunch of nuclei which are scattered within the reticular formation in the lateral tegmentum of the lower pons. The complex includes both named nuclei and multiple smaller unnamed nuclei. Some of the named nuclei include the lateral superior olivary nucleus, the medial superior olivary nucleus, which is the largest, retro-olivary nucleus, which is located dorsally, and the trapezoid nucleus, which is located medially. Now, coming to the cochlear nuclei, at the pontomedullary junction, on the posterior surface of the pons, a pair of dorsal and ventral cochlear nuclei will be located, lateral to the vestibular nuclei and dorsal to the inferior cerebellar peduncles. These nuclei belong to special somatic afferent column, and they receive the acoustic impulse or auditory impulse from the cochlear nerves. These dorsal and ventral cochlear nuclei have the second order neurons for the auditory pathway. So, like any other ascending pathway to the cerebral cortex, the fibers which start from here will cross the midline. So, those fibers which start from the cochlear nuclei and cross the midline, they form the acoustic striae. These acoustic striae take three routes. The fibers which begin from the ventral cochlear nuclei and traveling anterior to the spinal nucleus of the trigeminal, they form the ventral acoustic striae. These fibers, when they reach the midline, they decussate with the ventral acoustic striae fibers coming from the opposite side, and the decussating fibers will form the trapezoid body. After crossing the midline, they go on to relay in one of the superior olivary nuclei of the contralateral side. The fibers which start from the superior olivary nuclei will then ascend as the lateral lemniscus. There is a second set of fibers which start from the ventral cochlear nuclei. They pass posterior to the spinal nucleus of the trigeminal nerve, cross the midline, and join the contralateral lateral lemniscus, but without relaying in the superior olivary nuclear complex. Now, this set of fibers will form the intermediate acoustic striae. Similarly, there is a set of fibers which start from the dorsal cochlear nuclei, which will first pass on the posterior surface of the pons, then cross the midline and join with the contralateral lateral lemniscus without relaying in the superior olivary nuclear complex, and they form dorsal acoustic striae. So basically, ventral and intermediate acoustic striae fibers will begin from the ventral cochlear nuclei, whereas the dorsal acoustic striae fibers will begin from the dorsal cochlear nuclei. Some of the fibers traveling within the ventral acoustic striae may join with the ipsilateral lateral lemniscus without relaying in the superior olivary nuclear complex. So each lateral lemniscus is made up of the fibers coming predominantly from the contralateral cochlear nuclei, but it will be also carrying some of the fibers coming from the ipsilateral cochlear nuclei. Those fibers which did not relay in the superior olivary nuclear complex will go on to relay in the nucleus of the lateral lemniscus as they ascend within the lateral lemniscus. So with this knowledge, let us move on to learn about auditory pathway. The story of the auditory pathway begins in the cochlea of the internal ear. The hair cells within the organ of Corti are stimulated by the sound waves. Lower frequency sound waves will stimulate the hair cells in the apical turn of the cochlea. Higher frequency sound waves will stimulate the hair cells in the basal turn of the cochlea. These hair cells are the transducers, which will convert this mechanical stimulation into an electrical impulse, which is then carried by the cochlear part of the vestibulocochlear nerve. The first order neurons for this cochlear nerve will be located within the spiral ganglion, which is located in the internal ear. The spiral ganglion is made up of bipolar neurons. The vestibulocochlear nerve reaches the brainstem at the pontomedullary junction. The cochlear component will then relay in the ventral or dorsal cochlear nuclei, which will form the second order neurons. From the ventral and dorsal cochlear nuclei, the fibers which begin will either cross as ventral striae by crossing in the trapezoid body to relay in the superior olivary nuclear complex, or they cross as intermediate or dorsal acoustic striae without relaying in the superior olivary nuclear complex. All these fibers will ascend in the lateral lemniscus, and those fibers which had failed to relay in the superior olivary nuclear complex will go on to relay in the nucleus of the lateral lemniscus. When they reach the midbrain, they relay in the inferior colliculus. While most of these fibers, starting from the cochlear nuclei, will cross to the opposite side, ascend in the contralateral lateral lemniscus, and reach the contralateral inferior colliculus in the midbrain, some of the fibers may travel along with the ipsilateral lateral lemniscus to reach the inferior colliculus of the same side. From the inferior colliculus, the fibers will ascend as inferior brachium to reach the medial geniculate body, and from which is the part posterior to the pulvinar of the thalamus. And from the medial geniculate body, these fibers will continue as auditory radiation, passing within the sublentiform part of the internal capsule to reach the primary auditory area, otherwise known as A1 or area 41, which is located in the transverse temporal gyrus of Heschel, located on the superior surface of superior temporal gyrus, buried within the depth of posterior ramus of the lateral sulcus. So this is the entire auditory pathway. Now some of the extra features. The fibers of the right and left side will cross not only at the ventral, intermediate and dorsal acoustic striae, but fibers are exchanged between the two lateral lemnisci as well as between the two inferior colliculi. Now this is important in each cortex receiving binaural impulses, that is, it will not only receive impulses predominantly from the contralateral ear, but it will also receive impulses from the ipsilateral ear. This is important in localization of the sound. Second point, from the superior olivary nuclear complex itself, the fibers will be sent back to cochlea as well as to some of the motor nuclei, like motor nucleus of the trigeminal and the facial nucleus, which will then take part in the formation of acoustic reflexes like tensor tympani reflex or the stapedial reflex. Now these mechanisms will help in dampening the sound waves. And thirdly, from the inferior colliculus, there is projection to the superior colliculus. These auditory fibers reaching the superior colliculus will then travel within the tectobulbar or tectospinal tract, and this fiber pathway is important in turning your head and eyes to the source of sound. So some of the interesting features about the auditory pathway is that it has got more than 3 order neurons along its pathway. First order neurons are located in the spiral ganglion. Second order neurons are located within the ventral and dorsal cochlear nuclei. Third order neurons are located within the superior olivary nuclear complex or in the nucleus of the lateral lemniscus. Fourth order neurons are located within the inferior colliculus. Fifth order neurons are located within the medial geniculate body. So by the time the impulses reach the cortex, that the neurons in the cortex will be the 6th order neurons. So unlike other ascending pathways, which were predominantly 3 order neuron pathway, this has more than 3 order neurons along its pathway. Second interesting feature is it has got more than one site of crossing fibers across the midline, not only at the acoustic striae within the lower pons, but also the fibers are exchanged between the right and left sides in the lateral lemniscus as well as in the inferior colliculus. Now this is important for each cortex to receive information from not only the contralateral ear but also from the same sided ear, which will, as I said earlier, which will be important in localizing the sound. And third point is, throughout the pathway there is tonotopic arrangement. That is, the different frequency sound waves are located at a particular specified areas. This is seen in case of the cochlea itself, where the lower frequency sound waves are stimulating the hair cells of apical turn, and the higher frequency are stimulating the hair cells of the basal turn of the cochlea. The tonotopic arrangement will also be seen in the medial superior olivary nucleus. It will be seen in the central nucleus within the inferior colliculus. It will be seen in the ventral nucleus within the medial geniculate body, and it will also be seen in the primary auditory area. So within the transverse temporal gyrus of Heschl, the lower frequency sound waves will be located more anterolaterally, and the higher frequency sounds will be localized or represented more dorsomedially. Now coming to the cortical projections, this is the superior temporal gyrus. Its superior surface will be buried within the depth of the posterior ramus of the lateral sulcus. So that superior surface shows three areas from front to back. That includes planum polare, transverse temporal gyrus of Heschl, and planum temporal. The primary auditory cortex, or the primary auditory area, which is known as A1, or which is the area 41, is located in the medial part of the transverse temporal gyrus of Heschl. This is the area which is responsible for sound analysis and sound recognition. It has tonotopic representation and it has binaural representation. Injury to this area will result in cortical deafness, verbal auditory agnosia, and non-verbal auditory agnosia. That means the patient does not respond to any type of sound, so he is seemingly deaf. Although, mind you, the entire lower part of his auditory pathway is completely intact, so he does respond to some of the auditory reflexes, like sudden sound. He will turn his head and eyes to that source of sound, but he is otherwise unable to hear or make any sense of any other sound waves. Immediately behind this primary auditory area, located within the planum temporal, we have auditory association area, or A2, or area number 42. Now this area is involved in sound localization. It is also known that planum temporal is larger on the left side compared to the right side, so it may be involved in speech. Further posteriorly on the superolateral surface of the superior temporal gyrus, we have area number 22, or the Wernicke's area. This is the higher association area for the auditory pathway. Now this is involved in speech comprehension, wherein we understand the meaning of the spoken speech. So lesion to this area will result in sensory aphasia or word deafness, that is, patient is unable to understand the spoken speech. If it is written, he understands, but when it is spoken to him, he cannot make sense of it. From the auditory cortex, there will be projections to anterior frontal lobe, which is involved again in speech as well as in working memory and some of the executive functions like decision making. Two areas of interest here are the dorsolateral prefrontal cortex and the ventrolateral prefrontal cortex. Dorsolateral prefrontal cortex is involved in identifying where is the source of the sound, and ventrolateral prefrontal cortex is involved in identifying what is the source of the sound. From the auditory cortex, there will also be projections to the amygdala and entorhinal cortex of the parahippocampal gyrus. Now this is involved in emotional response to the sound as well as in memory and recall. With this, we come to the end of the auditory pathway. Hope you enjoyed this video. Thank you for listening patiently. You can visit this site for other neuroanatomy videos. Thank you.